3, 2, 1. Booster ignition. And liftoff.
More than half a century has passed since humanity left its last footprints on the moon. Artemis II is not just a return trip, but a rigorous test of the safety limits of modern technology. Artemis II is the first crewed flight of the Artemis program. The 4-person crew will fly around the moon aboard the Orion spacecraft using the SLS rocket, the most powerful system ever built by NASA. But here's the important part. A system in this configuration has never before been fully tested with humans. In everyday life, we're used to numbers, 1%, 0.1%, or even 0.001%. They seem small, almost insignificant. But in space, 1% can be the difference between life and death. In the aerospace industry, no one uses the word safe. Instead, they use a colder term, probability of loss of crew, LOC. This is the probability that a mission could result in the death of the entire crew. It's not a prediction, but a calculation based on thousands of failure scenarios. With entirely new systems like the SLS and the Orion spacecraft, current models show that the risk can range from 1 in 270 to 1 in 100. On paper, these numbers seem very low, but in a real-world context, they have a completely different meaning. If a commercial flight had that level of risk, no one would dare board it. But in space, people accept it, not because they downplay the danger, but because they understand that every great advance involves calculated risks. In 1967, during a ground test, the Apollo 1 spacecraft caught fire in the matter of seconds. 3 astronauts, Gus Grissom, Ed White, and Roger Chaffee, were trapped inside a sealed cabin filled with pure oxygen. The fire spread so quickly that they had no chance to escape. This accident did not occur in space, but on the test pad, yet it made one thing clear. Risk exists not only during flight, but throughout the entire system. Nearly 2 decades later, in 1986, the Space Shuttle Challenger exploded just 73 seconds after liftoff. The cause began with a seemingly minor detail, an O-ring in the booster rocket that failed to function properly due to low temperatures. Hot gas leaked in, destroyed the structure, and in an instant, the entire spacecraft disintegrated. 7 astronauts died. A small deviation within what engineers considered acceptable turned into a catastrophe. In 2003, history repeated itself with Columbia. During launch, a piece of insulation material from the fuel tank struck the spacecraft's wing, causing damage that no one considered serious. But when the spacecraft re-entered the atmosphere, temperatures of thousands of degrees penetrated that weak spot, destroying the structure from within. The 7 astronauts on board had no chance of survival. Once again, it wasn't a major error, but a chain of small deviations that weren't properly assessed. However, Artemis II carries an even greater challenge. This is a mission with new technology, a new configuration, and an operational environment that extends beyond Earth's orbit, where humans have very little real data. That means all probability calculations contain a blind spot, where no one can be sure that every scenario has been considered. And then comes launch time. When Artemis II leaves the launch pad, all the models, numbers, and complex calculations stop. There are no more simulations or predictions, only unfolding reality. At that moment, probability ceases to be a statistical value and becomes a possibility that can occur at any instant. Upon exiting low Earth orbit, LEO, the Orion spacecraft must pass through the Van Allen belts, two enormous regions of radiation surrounding Earth, where charged particles, protons and electrons, are trapped by the planet's magnetic field. These particles move at speeds close to that of light. As they pass through the spacecraft's hull, they can damage the astronaut's DNA or cause failures in sensitive electronic circuits. The Orion spacecraft will travel at an extremely high speed to cross this region as quickly as possible in order to minimize the total accumulated radiation dose, total ionizing dose. Previous Apollo missions traversed this zone along trajectories calculated with extreme precision to reduce exposure time. But even so, the risk was always present. Artemis II will also have to undertake a similar journey, where every minute represents a balance between speed and safety. Once they have passed through the Van Allen belts, the crew will face an environment without the protection of Earth's magnetic field. These are atomic nuclei, such as iron and nickel, stripped of their electrons, arriving from outside the solar system with extremely high energies. They're like microscopic bullets that pierce through everything. Protecting against GCRs is extremely difficult because when they collide with the spacecraft's metal hull, they generate even more dangerous secondary radiation. Even more dangerous are solar storms. Unlike cosmic rays, which are constantly present at background levels, solar storms occur suddenly when the sun releases large amounts of charged particles in a short period of time. If an intense solar storm occurs while the spacecraft is heading toward the moon, the astronauts could suffer acute radiation sickness, which can cause nausea, exhaustion, or even death if they do not have a safe shelter. When the Orion spacecraft flies toward the far side of the moon, the massive rocky mass will completely block all radio signals to Earth for about 30 to 45 minutes. During that time, the crew will be completely on their own. If an engine or system failure occurs, Earth won't know anything until the spacecraft reappears from the other side. Unlike the International Space Station, ISS, where astronauts can return to Earth within hours in the event of a medical emergency, Artemis II takes humans thousands of times farther. Once the ignition maneuver to enter the trajectory toward lunar orbit is performed, the spacecraft takes at least 3 to 4 days to return. Any critical system failure during this phase turns the surrounding space into a dead zone, as there is no rescue spacecraft capable of arriving in time. To address these risks, NASA has designed special measures. In the event of a solar storm, the astronauts will take shelter in the central part of the capsule, using food bags and heavy equipment around them to create an additional layer of protection against radiation. The Hera system and portable radiation measurement devices allow the crew to monitor exposure in real time. The Orion spacecraft's hull is made of hydrogen-rich polymer materials, capable of blocking radiation better than traditional aluminum. Understanding the probability of risk in these dead zones is key for engineers to optimize response scenarios and ensure the safety of the 4 astronauts on this historic journey. This pressure is not limited to the crew. It extends back to the families, those who aren't boarding the spacecraft but must live with all the worst-case scenarios. When Reed Wiseman was informed he would command Artemis II, his first reaction wasn't pride or excitement, but the weight of responsibility. As a single father, he understood that this flight wasn't just a scientific mission, but a decision that could directly affect the future of his two daughters. According to psychologist James Picano, who's responsible for supporting astronauts' families at NASA, the real pressure doesn't begin on launch day, but long before. The Artemis II crew was announced in 2023, nearly 3 years before liftoff. That long period isn't a passive wait, but a continuous sequence of training with an intense schedule, combined with unpredictable changes and delays. For families, this means living in a prolonged state of tense waiting, where daily life is constantly interrupted by the demands of the mission. It was only after the Apollo 1 disaster in 1967, when 3 astronauts died in a fire during a ground test, that NASA began to more systematically develop psychological, medical, and financial support systems. After the Artemis II crew completes its exploration of the far side of the Moon and begins the return journey, the spacecraft will be like a stone hurled toward Earth at extreme speed. This speed is 30 times the speed of sound. At that speed, Earth's atmosphere ceases to be soft air and becomes as rigid as a concrete wall. If the entry angle is too steep, the spacecraft will be crushed by extreme pressure. If it is too shallow, it will bounce back into space like a stone on water and drift away forever, where the crew will run out of oxygen. Temperature: 2,760 degrees Celsius, almost half the temperature of the Sun's surface. The layer of Avcot material covering the underside of the spacecraft is designed to gradually burn away, ablation, and dissipate heat. However, on the previous mission, fragments of the material broke off in chunks rather than wearing away uniformly. If the Artemis II heat shield suffers large detachments as before, extreme heat could penetrate the structure, damage computer systems, or directly endanger the astronauts' lives. When the spacecraft travels at supersonic speeds, friction turns the air into plasma, ionized gas. This plasma layer surrounds the spacecraft and blocks all radio signals. For about 6 to 7 minutes, the crew is completely cut off. Earth has no way of knowing whether they are still alive or not. If a problem arises, for example, if the parachutes fail to deploy, the astronauts must resolve it on their own, without assistance from the ground. After 10 days floating in space, the astronauts' bodies weaken. During re-entry, they will be subjected to gravitational forces 4 to 5 times their body weight. This can cause pain, difficulty breathing, or temporary loss of consciousness just when they need to monitor the landing systems. The Orion spacecraft requires 11 parachutes to deploy in perfect sequence to slow down from 500 kilometers per hour to 30 kilometers per hour. If one of the main parachutes fails, the impact with the water would be equivalent to a severe car crash. If the waves in the San Diego area are too high, the capsule could capsize. The astronauts would be suspended upside down inside the cramped cabin, waiting for rescue teams for 30 to 45 minutes. They have traveled farther than any human in history. They have seen the dark side of the moon with their own eyes. But the true victory lies not in those breathtaking images, but in 4 people emerging alive from the capsule. Every mark on the heat shield is a hard-won lesson so that the Artemis III mission can actually set foot on the lunar surface in 2027. Although they know that the estimated risk of 1 in 40 might be lower than the actual one, they still decide to board the spacecraft. The mindset of these exceptional individuals is not to ignore the danger, but to assess it clearly. The value of exploration is worth the price. The actual probability that they will not return is a number that no one can know with certainty. But the reason they go anyway lies not in cold statistics, but in the deepest essence of the human being. We are the only species that looks into the infinite void, calculates the price to be paid, and decides it is worth it. That is why today we are moving toward the moon, and tomorrow, perhaps, toward Mars. Because in the blood of humanity, the desire to understand is always stronger than the fear of death.